already. If you're here, please let me know you're here. Make yourself known. I want to say hello to Janice, as well as C. Jones and Kiri saying hi. Hello, everyone. So happy that you're here today. And pretty much what we're going to be talking about is a bunch of different topics that are going to be so beneficial for you. You know, I always see that this live show that I'm doing it's pretty much worth $100 worth of tutoring, but you guys are getting this absolutely free. And it's basically my way of sharing my knowledge and everything that I, went through in college and want to teach you the shortcuts and teach you the best ways to actually understand chemistry. I see more people coming in, and Ryan says hello. What's up, Ryan? And Madison is saying hello as well. So is Reedy, and then Marine. Flores is also saying I know you guys are asking questions. I'll get to that as well. Hey guys, so thankful that you guys are here. So by the way, I will be going over so many different topics today. If you aren't familiar, I see some people are putting in other questions. So I actually pre-select the questions ahead of time. The reason why I'm doing that is just so I could actually create this lesson plan for you and answer as many questions as possible during the duration of this hour. So if you want a chance to get your questions answered, tweet me. So you can tweet me at hello Melissa M, and then you can also put the hashtag of Ask Melissa Maribel, and then tweet me your chemistry question, take a picture of it or type it out, or even just the topic that you need help with. And then the following Sunday, I will pick from those different tweets, and then that's how I create my lesson plan or what I choose to teach today. So that's what I'll be talking about today. I also want to mention that I have so many links in the description box that are beneficial for you, whether it be I'm actually going to be going into a lot of different formulas. So I have a formula sheet that is there for you, that you can download. It's for chemistry 1 and 2. So highly recommend downloading that. That is my gift to you. I also have other links towards the bottom that I personally actually used. So it's going to say that it's Chegg Study or Chegg. I personally used that all throughout college. I was a chemistry major, if you aren't familiar, and I went through so many math classes, physics classes, and chemistry classes. It was a lot, but Chegg got me through it and actually really helped. The homework help was so beneficial for me. So I really recommend checking that out. I do want to mention, though, a little disclaimer, I am an affiliate partner with Chegg. That just means that I get a tiny little bit if you do click the link, and all of that goes to the props of my channel or just making more videos for you guys. Okay, so just want to mention that. All right, why don't we start with resonance structures? So at the end, after this is done, or if you're watching the replay, then I will put a pinned comment telling you exactly what time or like timestamps the resonance structures are, hybridization, and so on. So make sure to check that out after. Okay, so we'll start off with resonance structures. We'll talk about hybridization, sigma and pi bonds, and then at the end, we'll do standard enthalpies of formation. Let's start off with resonance structures. Now, the main thing here with resonance structures is, before we even get into that, Lewis structures, right? So you need to know how to draw a proper Lewis structure before you get to drawing all the resonance structures or even to hybridization. So the first thing that I want you guys to remember and to memorize is where your valence electrons are. So valence electrons, real quick, all that is, it's basically just the electrons on the outermost shell of an atom. And the main thing I want you to know is what everything is. So your valence electrons, for your first group is 1, second group is 2. We don't know for transition metals because those vary, they change. And then for this next row, it's 3, 4, and we keep going, 5, 6, 7, and 8. All right, so that's going to be extremely important to know and memorize for your next exam for Lewis structures or resonance structures and so on. All right, so that being said, let's practice drawing our resonance structures or Lewis structures. So I already found the total amount of valence electrons, but we'll go over it together. So first things first, when we're drawing Lewis structures, remember with Lewis structures, the main one that you're going to see is that your electrons are actually being shared with one another. And then if we remember this, here, let me actually draw this out. 2 electrons or 2 dots is going to form one bond. Okay, so one single bond. And then rather, if we were to keep adding electrons, so let's say if we had 4 electrons, that means it's actually a double bond. And if we had 6 electrons, that forms a triple bond. Okay, so that's going to be beneficial to know. That's just kind of going way back to Lewis structures. Okay, so what I always want you to think of with Lewis structures is how many valence electrons in total do we have when we're given this molecule or compound? Okay, actually molecule in this case because it is covalent. So for nitrogen, that's going to be 5. And then that goes back to what I showed you previously with how many valence electrons there were, okay? So nitrogen had 5, oxygen has 6 valence electrons, but how many oxygens are there? There's 3. So that's why I had to multiply it by 3, and then we'll get 18. Next, there's one more thing here. Because there's a charge, and especially because there's a negative charge, instead of subtracting from the total amount of electrons, you're actually adding. Remember that electrons are negatively charged. So if we have something that is negative, that's actually adding or becoming even more negative. So that's why we're adding 1 to the total amount of valence electrons, which actually gives us 24. Okay, next step is to identify what your central atom is. In this case, there's only going to be 1 because nitrogen is by itself, and then oxygen, since there's 3 of them, that's surrounding the nitrogen in the center. So I'll put nitrogen in the center, and then I'll put 3 different oxygens surrounding that nitrogen. Okay, next step is to start to bond everything together. So because it's a covalent compound, and how I know that, remember covalent just means it's nonmetals, okay? So it's only nonmetals, there's no metal and nonmetal, it's just nonmetals. So then I know that everything has to bond regardless because that's what a Lewis structure does. So I'm actually going to just put a bond right now. That's how I typically like to start this. Everything has a bond towards that central atom. And then from there, I'm just going to start adding more electrons. Before I do that, I want to teach you a trick that helped me and a lot of my students. So if I were to have a single bond, and let's say with something like oxygen or any sort of halogen like fluorine, chlorine, iodine, and so on, and bromine, think of it as if we have one single bond, we would then have 3 different lone pairs. Okay, and then these are the lone pairs that I'm talking about. So 2, 4, and 6. Missed one. There it is. So then if we had, let's say, a double bond now, that took away one of our lone pairs. So we instead only have 2 pairs or 2 sets of lone pairs. And then now if we had a triple bond, we only have 1 lone pair. So this is always going to be the trend for really all of these types of things that I'm going to be going over, especially oxygen. Oxygen is a common element that you're going to see in Lewis structures. So that's my little key for you. So then what I'm going to do here is, since every single one of these has a single bond, I'll put 3 different pairs of electrons or lone pairs. So then that's what I'll have so far. Next step is to just double check if we have a full octet. So a full octet, what that means is we have 8 valence electrons or 8 electrons surrounding the central atom, because that's what makes it the most stable. So let's double check. Let's see if we have that. If I were to count up all of the electrons surrounding nitrogen, I would have 2, because remember, one line, one single bond counts as 2 electrons. So 2, 4, and 6. So no, we don't have the total amount of valence electrons or complete that full octet, all right? We don't have that octet. So in this case, because we don't have that full octet, but if we actually noticed, we do have the total amount of electrons as 24. So let me actually go back to that. Let me go back to what I was talking about there. With our valence electrons, we had 24 in this total molecule, right? And then if we counted everything up, we actually did have 24. And because we would have had 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. A trick for you here is to see that this entirely is 8, right? This is 2, 4, 6, 8. So if this is 8, multiply that by 3, and we'll get 24. So then that tells us, okay, we have the total amount of valence electrons, but in this case, we don't have the full octet, right, for nitrogen. So instead, what I have to do is I have to actually change one of these single bonds to a double bond. I'll move this top electrons, or this lone pair, doesn't matter which one I choose, by the way, and I'll move that to form a double bond. So now instead we'll actually have a double bond, but we don't have all 3 lone pairs because we moved that down to get that double bond. And that's kind of like going back to this little key of this guide. All right, so then because only one single bond has 3 lone pairs, 2 bonds has 2 lone pairs, 3 single bond, or actually, sorry, a triple bond has 1 lone pair. So that's how I want you guys to kind of think about it. And then everything else will stay the same since we don't need to move anything else. And we'll check that. All right, so now checking nitrogen and seeing, does it have 8 valence electrons? So here we have 2. This is actually 4. Remember, 4 electrons here. So 4 plus 2 is 6, plus an additional 2. So 6 plus 2 is 8. This completes the octet rule, so it is stable, it is happy. Last thing with this is whenever we have something that is charged, so right, we have that charge, you have to put the entire structure in brackets and place the charge on the outside. So that's what we would do for this overall Lewis structure. But we're not done yet because we're talking about resonance structures. So let's keep going. Let's see if we could have drawn this a different way. So I'm going to bring this back and just draw it again over here. Okay, so what we had previously in the very beginning was everything had a single bond, and we had 3 lone pairs on every single oxygen. What if I didn't choose this top oxygen to get the double bond? What if I instead chose, let's say, the one on the left or the one on the right? So either of those would have been correct. So, and it would have really been the same exact sort of structure. You're just moving the double bond around. So that's exactly what I could have done. I could have done this way. I could have moved this here, or I could have moved this one here. Or what we did previously in the very beginning, we moved these electrons here. All right, so because there are 3 different oxygens, we are most likely going to have 3 different resonance structures. But I don't want you to always think that. I always want you to check first before, because there are some exceptions to the rules, right? That's chemistry, I know. But this is kind of my way of seeing, okay, if I can move one of the double bonds, can I move it to another oxygen, and so on. So in this case, we'll have another one. So this is our other structure, or resonance structure, with all the lone pairs. Once again, we'll put this in brackets and put a negative charge on top, just because that was the total charge of our molecule. I'll do the same thing. So now I'm approaching this purple one, and the double bond will go on the right oxygen, but everything else will stay the same. Okay? So that's essentially, and in brackets with the negative charge. So that's essentially what we would have. Let's see all of them. So remember that resonance, essentially what this is saying is that if you have your Lewis structure, or if you have your molecule, it can be drawn multiple ways. Okay, so it could have, I've seen some that have 6 resonance structures, some that only have 2 or 3. It's really just dependent on the structure that you're given initially, and how many oxygens or how many, elements you're given. Now, with this, you'll note that they have to have a valid structure. And what that means, remember, a valid structure is based on the octet rule. Okay, so if it obeys the octet rule, if it has to, which in this case it does, then it has to be valid. It's a valid structure if it obeys the octet rule. Okay, in this case, because nitrogen and oxygen do obey the octet rule. So that's essentially what I want you to think of. Plus, we're going to have something else that's called formal charges. All right, so I know there's a lot to this topic overall. Right now, what I'm covering, guys, if you're just joining me, is I went over a little bit of Lewis structures, and now I just talked about resonance structures. Now I'm going to dive into formal charges. So the reason why I'm going to get into formal charges and why they're so beneficial is because let's say you aren't sure which structure is correct, if the structure is actually valid. So formal charges help you see, is this a valid structure? Is this the best structure? Did I draw it right? All right, so that's like your little checker right there, okay? So for formal charges, the formula is going to be based on however many valence electrons we have. So valence electrons of, let's say in this case, nitrogen. So if we were to look at nitrogen, what are the typical valence electrons? Well, that's 5. So I have 5. minus the total bonding electrons. And what that means, bonding electrons are essentially the electrons that are touching that atom that we're looking at, which in this case is nitrogen. So the ones that are directly touching that nitrogen are 1, 2, 3, and 4. So there's 4. Now, remember that one single line or one single bond has 2 electrons, right? So, and this would have 4. So I'm just looking at the ones that are directly touching whatever atom I'm finding the formal charge of. So I'm going to keep going and I'm going to see, okay, well, I still need the individual lone pairs. So I'm going to add the individual lone pairs, which in this case, nitrogen doesn't have any lone pairs, right? It's a central atom, doesn't have anything. So I'm going to say that's 0. So in this case, this would have given us a positive 1 after we subtract everything. So nitrogen would have been a +1 in the center. And then I can keep going and see, all right, what would this be if I were to do, let's say, this bottom oxygen? Well, the valence electrons of oxygen, the typical ones, are 6. I'm going to subtract that, and I'm going to look at however many bonding electrons we have. The only bonding electrons, right, the bond, is this blue one right here. There's only 1 electron that's directly touching that oxygen. So that's why it's 1. And then I'm going to add all of the lone pairs that we have. So, and by the way, it's not the actual pair, it's each individual electron or each individual lone pair. Okay, so here we have 2, 4, and 6. So that would have been 6. And then 6 minus 7 would have been a -1. So this would have been a -1 for our formal charge. And if we keep going, this would be the same exact thing because nothing changed. There's no double bond. There's the same amount of individual lone pairs and bonding electrons. Now, the next one on top right here, I'll do that one. So same thing. The valence electrons is 6 for oxygen. I'll subtract this, and our bonding electrons are 2 of them, right? They're the electrons directly touching that atom or oxygen. So that would have been 2 plus the individual lone pairs, so 2, 4. And then in this case, this gives us 6 minus 6, which is 0. So this would have been a 0 for our formal charge. And then you'll note that all of these are going to end up being the same. Like if we were to do this again, this would have the same formal charge of +1, of +1, of -1, 0, -1, and so on. So that's what I mean when it's a Lewis structure that's drawn in different ways. It is a valid structure because 1, it does obey the octet rule, and 2, their formal charges are also the same. So that's essentially the concept of resonance. That's making sense. Let me know if this is making some sense, guys, if you're still with me. So I want to do this again. Now, in this case, we'll focus on finding which structure is the best structure. So I've seen a lot of cases and exam questions, so be aware of this question. It's either going to be OCN or HCN or SCN. I'm telling you, I've seen this everywhere. But they're going to ask you which structure is the most favorable or which structure is the most stable, which structure is the best structure, okay? So that's typically how they word it on an exam or a quiz or even a homework question. So what we have to do is we have to figure out how can we draw this same molecule, differently. And 1, is it a valid structure? We're going to base it on the formal charges. The formal charges are going to tell us, is this the best structure? And I'll explain how you know it's the best structure using the formal charges. Let's just start with doing more Lewis structures, okay? So let's just identify how can we draw this. And then first things first, as always, we always have to see how many valence electrons we have in total. So in this case, oxygen has 6, carbon has 4, and nitrogen has 5. But we're not done yet, right? We still have this, let me bring that back. We still have this -1, and we're actually adding 1. So I have 15 on the bottom. I can't get to it, but I'm going to add that. So +1. Okay, so whenever it's a negative charge, we're always adding to the total amount of valence electrons. So this would have been 16 total electrons. Okay, now let's keep going. We have multiple I actually wouldn't say multiple central atoms, but it seems like we could have multiple central atoms, okay? So if you're not sure what the central atom is, it's going to be based on whatever is the least electronegative. So let's go back to what electronegativity is. I know Lewis structures tends to put everything that you've previously learned together. Remember that fluorine is here, So electronegativity, that's essentially saying how strong the element is to attract another electron. That's essentially the concept, okay? So whatever is closest to fluorine is going to be very electronegative because our trend increases as we move from left to right and then as we move up a column. So in this case, whatever, like I mentioned, whatever is closest to fluorine is going to be very electronegative. Whatever is furthest away from fluorine is going to be not so electronegative. So in this case, if we're looking at the different atoms here, which one would be the least electronegative? And whatever's the least is our central atom. So if I were to draw where, oxygen, carbon, and nitrogen are, that would have been, and I feel like I ran out of space already, but this would have been, here, I'm going to redraw this part here. So this would have been CNOF, okay? That's just on the periodic table. So oxygen cannot be our central atom since it is the most electronegative. Nitrogen can't either. It's also very electronegative compared to carbon. Carbon is the least electronegative, so that's going to be your central atom. Another little hint is carbon. If carbon is in your molecule, it is your central atom. Carbon is one of the best central atoms to have. It is very stable, so just a little note there. And then what I'm going to do is I'm actually going to put oxygen and nitrogen on the opposite sides, okay? So this essentially already has it written in the correct order for us, okay? So then the next thing I'm going to do, I actually think I had it. Yeah, I did. Cool. So that's the specific order. Let me see if I can. Perfect. Next thing I'm going to do is actually add the bonds in between. All right. So adding the bonds, I'll add one single bond on either side, and then I'll start adding electrons on the outside. Okay. Then I'll make my way in and double check, does this obey the octet rule? So I'll add my lone pairs on the outsides. And let's just double check if we have 16. Remember my little trick that I mentioned was this is 2, 4, 6, 8. So if this is 8, then the opposite side is also 8. 8 times 2 or 8 plus 8 is 16. So that's a check. Yes, we have that. But carbon doesn't have 8 electrons, so it doesn't obey the octet rule. So that's what we need to fix right now. This only has 2 and 4. We need 4 more electrons or 2 more bonds. What we could do is we can actually move these electrons here to form a double bond, and same thing here. We can move those electrons to form a double bond there. So what we could do now, or what we could have, is this as our structure. Next thing, remember I talked about if this is, and I think it's not going to show. Darn. There has to be brackets. Let me see if I can make this a little bit prettier. There we go. So there has to be brackets, right? And then with a negative charge. So has to be brackets with a negative charge if our overall molecule has a charge, okay? So what I want us to do now is identify the formal charges of everything. So let's start off with oxygen. So let's do I'm going to say Fc of O. That just means formal charge of oxygen. And then what we're going to do first is have the valence electrons of oxygen. So remember that's 6 minus, I'm going to put this in parentheses or brackets, minus the bonding electrons. So our bonding electrons are whatever is directly touching that oxygen. So 1, 2. I'm going to add that to the individual lone pairs or individual electrons. So here we have 2, 4. And then this is going to give us 0. So this has a formal charge of 0. And then next, our central carbon, that's what I'm going to do now for our formal charges. So formal charge of carbon. And then carbon has 4 valence electrons. Next, I'm going to go back to the overall bonding. Let's do this in a different color. So carbon has 1, 2, 3, 4 bonding electrons. But there are no individual lone pairs at all on carbon, right? So that's 0. And then 4 minus 4 is also 0, so this is 0. And then next, we'll do nitrogen at the end. So nitrogen has a formal charge, has a valence electron of 5, right? There's 5 valence electrons. Now I'm going to subtract this from our overall bonding electrons, which is 1 and 2. And then next, I'm going to keep going and add that to the overall individual lone pairs or electrons, which we have 2, 4. And then this would have given us 5 minus 6, which is a negative 1. All right. So by looking at this, I could instantly tell this is wrong. And the reason why I know that is because the most electronegative atom wants to be negative. And remember, which one was the most electronegative? It was the oxygen, right? Because that's the one closest to fluorine. So if you ever forget, oh, what's the trend for electronegativity? Just think whatever is closest to fluorine, that's going to be the highest in electronegativity or the most electronegative, okay? So in this case, the reason why this is wrong is because oxygen should have been negative, but it's neutral, it's 0. So this structure, no, okay? So that is not the best structure. So we'll try this again. Now, we could have drawn this a little bit different, and I'll put this on top. So instead of having 2 double bonds on either side, what if we were to have a triple bond? And let me bring back all those electrons. Okay, so what if we were to have a triple bond on the oxygen? Okay, so I'll put a double bond here and a triple bond here. And when I do that, that essentially gives me this structure. Okay, so I'll show you how I did that again. So the reason why I did that, remember, we have to have we have to complete that octet rule. So this gives us our full octet. Let's go over that again. So carbon has 2, 4, 6, 8, right? 8 valence electrons in the central atom. That's happy. That completes the octet rule or obeys the octet rule. So now it's valid. But we're going to double check once again our formal charges and see, is the most electronegative atom negative? So let's do that. And then one more little thing, remember that this has to be in brackets with a negative charge, just because this has a negative charge. Okay, let's do this all over again. So for oxygen, we'll find the formal charge of oxygen. Our valence electrons are 6. I'll subtract that from the bonding electrons, which is 1, 2, 3. Next, we'll have 2 overall electrons. Okay, so I'm going to have 2 electrons here, and that's 6 minus 5, so that is a plus 1. So that's plus 1. I'm already going to stop. And the reason why I'm going to stop, because the most electronegative atom is positive, that should be your red flag saying, no, this is wrong. So there's possibly one more structure. So remember, as I mentioned again, the most electronegative atom wants to be negative, okay? So especially and this is specifically actually in a charged molecule, like in this case, that this is negative, all right? So let's do this one more time. And I like how it had it already. Let's do this one more time, but here. We could have moved this to the opposite side. So instead of oxygen, we could have had a triple bond on the nitrogen, which is essentially what we see here, okay? So once again, I'll put this in brackets with our charge on top, and then we'll put our formal charges. All right, so let's start off with oxygen again. Formal charge of oxygen, there's 6 valence electrons, and then how many bonding electrons? So this is only 1, okay? Then I'm going to add however many individual lone pairs we have. So this is 2, 4, and 6. So this gives us 6 minus 7, so that's negative 1. So far we're on the right start because our most electronegative atom is negative. And then now we'll do the same thing for carbon. Formal charge of carbon, remember valence electrons are 4. And then we have how many bonding electrons? There's 1, 2, 3, 4. There are no lone pairs, so this gives us 0 as our formal charge. And lastly, if we were looking at our formal charge of nitrogen, there are 5 valence electrons, and then we have how many bonding electrons? There's 1, 2, and 3, because those are the ones directly touching that nitrogen. So there are 3, plus how many lone pairs? 2. So that gives us 5 minus 5, giving us 0. So that's 0. And you'll also notice that your formal charges, if you were to add them all up, it actually equals the overall charge of this entire molecule, which in this case is negative 1. And we'll see that here, like our first formal charge is negative 1, plus that 0, plus another 0. And that equals the overall charge, which is negative 1. Okay, so that's another way that you know that you did it correct. So this is actually the best structure. Why? Because, excuse me. So the reason why we know that is because the most electronegative atom is negative, as well as if your central atom can be zero, if it can be neutral, it's happy that way. It's stable that way. So let's see. All of these that we just mentioned, the best structure, and all of these have brackets, by the way, with a negative charge. I think I ran out of space here. So then this is the best structure. My hint to you, because I see this all the time, as I mentioned, on exams, is whenever you have something with like cyanide, which is CN, remember that cyanide is always going to have that triple bond between the carbon and the nitrogen. Because I've seen this for, goodness, I've seen this for HCN. I've seen this for SCN, I think minus, and then OCN minus. So I've seen all of these, and the structure that is always the most favorable is the one that has that triple bond between the nitrogen, okay? And then the hydrogen or whatever atom we have there, okay? So that is my hint to you if you ever see this on an exam or a quiz question. All right, so we're going to keep going and see what we can do next. So I'm going to be talking about hybridization. I'm going to see what everyone is saying, how we're doing right now, guys. For everyone that's kind of joining in, and I know there you guys still have different questions. If you're not familiar with how this new sort of live show is working, what I'm doing before is I'm actually pre-selecting the questions using Twitter. So you guys tweet me your questions for a chance for me to answer them in the next live. And then that's how I'm actually choosing these questions or these topics. So, because people already initially tweeted me throughout the week. So if you really want your question to be answered, tweet me, okay? So that's what I highly, highly recommend. Another thing that I also wanted to mention, there are so many resources that I have for you throughout the description box. And I always put this, by the way, in every single one of my videos, in every single live. I always put the free chemistry survival guide that I made for you. It's both chemistry 1 and 2. You can go ahead and download that. That just has all the formulas, these awesome tables that I have right now on hybridization and electron geometry. That's there too. It's basically every sort of table, formula, constant, anything that I can possibly think of that would be beneficial for you to have and to just know I put it there. All right, so you can see that in the description box. Another thing that I personally want to mention is in the bottom of the description box, you'll find other links that actually go out to Chegg. And the reason why those are there is because I personally use Chegg Study all throughout college. It helps me so much, and I highly recommend it for you guys if you want to check that out. It basically is a great way to help you understand your homework. I know I personally had issues understanding every single homework problem, so it was nice to just be able to go there and see like the step-by-step explanation and help me understand my homework and really chemistry even better. So I highly recommend checking that out. It is in the description box. And then just a little disclaimer, I am an affiliate. I am part of the affiliate program, so I do get a tiny little commission if you do click the link. And all that goes to is helping me basically fund my channel to be able to make more videos for you guys. As you see, I do have plenty of props, and I try my best to make it as fun and entertaining as possible. So that just goes to that. Okay, so let's keep going to hybridization and what this all means. So hybridization, what this essentially is talking about is how orbitals are overlapping. So this is going to tie into Lewis structures and geometry, like the electron geometry. And then I'm going to talk about those two different things right now if you don't remember what electron geometry is or what molecular geometry is. So the main two differences with electron geometry and molecular. Electron geometry is going to tell us how many electron groups there are. So let me explain that. So these are the different electron groups, right? We could either have 2, 3, 4, 5, or 6. And what this essentially is saying, if you'll see on the bottom, it states that electron groups are our bonds plus our lone pairs. So that's how we define electron groups. Remember that a single bond counts as 2 electrons. And then we said a double counts as 4 electrons. A triple bond counts as 6 electrons. So that's what I'm talking about. That's what I'm talking about here when I'm talking about electron groups. Okay, we could also see that here with electron groups. There's 2 bonds, that's why it's linear, 3 bonds, that's why it's trigonal planar, and so on. For molecular geometry, that's going to tell you more specifically on the shape of the overall structure. That's why sometimes you'll see, I remember there's one that literally says it's like T-shaped because it looks like a T, or it is bent because the actual, whole entire structure is bent. So that one goes specifically to how the overall shape of the molecule looks like, rather than electron geometry goes more into how many electrons are surrounding that central atom or how many electron groups. So we'll do that together, don't worry. Now, for hybridization, there is a beautiful table here that I highly recommend you guys know because it makes it so much easier to just figure out what is the hybridization of that atom that you're looking for. So we'll go over electron groups, and if it has 2 electron groups, it's linear, so our hybridization is sp, and we'll keep going. If it's 3, trigonal planar, so it's sp2. Tetrahedral, which is a really common one, is sp3, trigonal bipyramidal, sp3d, octahedral, sp3d2. Okay, so that's pretty much the highest that you guys will see in this class. But this table is going to be really helpful. Let's put it into practice. Let's say if we had two different examples, and I'll start off with CH4. What I would want to do first is just count how many electron groups there are in total for that central atom of carbon. So what we'll do, we'll just count. Because electron groups are our bonds plus our lone pairs, you'll see that your central atom doesn't have any lone pairs, so I don't need that. But I'm just going to look at how many bonds are there. Well, there's 1, 2, 3, and 4. Because there are 4 bonds, I'm going to say there are 4 electron groups. And because there's 4 electron groups, that tells me it's tetrahedral. Now, how I'm going to use my hybridization table is because I know the electron geometry is tetrahedral, I can then go and see, oh, then that means our hybridization is sp3. And that's exactly right. Our hybridization is sp3 for that central atom of carbon. And I'll do this again. I'll do this for this next one. And once again, I'll identify how many electron groups there are. And it's our bonds plus our lone pairs. So we have 1, 2, 3, and 4, including the lone pairs. So once again, we have 4 electron groups. That tells me, once again, it's tetrahedral. We said tetrahedral was sp3. So this is also sp3. So those are just 2 good different, representations of what sp3 can look like. And don't worry, we'll keep going. We'll do this again. All right. And by the way, if you are liking all of these little examples and all of these explanations, I actually put in the chat the Lewis structure notes. You can find that there. If you would like to shop my notes, I also have more than just Lewis structures. I have naming compounds or stoichiometry, limiting reactants, a lot of different things that will be really beneficial. Think of it as a how-to guide on that specific topic, and I explain everything in detail with helpful things that I personally recommend, just because I've seen so many chemistry exams over the years as a tutor. So I know what teachers are typically saying, or even the same questions, I use them there. Okay. So that's what I have in all of my note packs or whatever you want to call it, those ebooks that I have. Okay. So awesome. Let's keep going. We're going to see that this is another type. So if we want to find the overall hybridization of phosphorus or sulfur in this case, so let's start with this one. If I want to find the hybridization of phosphorus, then I'm going to count how many electron groups we have. So right now we just have bonds. So there's 1, 2, 3, 4, and 5. So since there's 5, I'm going to go here and see, oh, okay, well, 5 is trigonal bipyramidal. That must mean that it's sp3d. And then I'll do this again, and I'll see, okay, what about this one? This has 1, 2, 3, 4, and 5. So since that has 5, it's going to be the same thing. It has 5 electron groups, so I know that this is sp3d. All right, so that is just a helpful way. If that's making sense, let me know if it is, guys. So this is really just following the table and knowing, all right, how many electron groups do I have? Then from there, you piece it together and the table will tell you what that hybridization is. All right, so I do highly recommend knowing that, okay? All right, so I want us to keep going because I don't want to run out of time. And we're going to go to just sigma and pi bonds. Then after that, after sigma and pi bonds, we're going to actually do a hybridization question where you have to draw the actual orbitals and seeing how everything's overlapping. Okay, so that's what we'll do. And then at the end, we'll answer one more question on standard enthalpies of formation. All right. And then thank you, Ryan. That was really sweet. Ryan just said, I wish Melissa was my personal tutor. Thank you. Thank you. Well, I'm here now. So with sigma and pi bonds, what I want you to know, and this is kind of like this little shortcut or little shorthand thing, where a single bond is a sigma bond, okay? And then let's just show what these symbols look like. So sigma looks something like this, all right? So that is represented as a sigma bond. If it's a single bond, it's a sigma bond. And then now a double bond is going to consist of one sigma and one pi. So that is going to be kind of like your shorthand, is just to know, all right, if I see a double bond, I automatically know there's a sigma and there's a pi bond. But if we have a triple bond, then we're going to have one sigma and two pi bonds. All right, so know this, really, it's going to be really beneficial because I've seen a lot of questions where they ask, and these are like easy points, where they ask how many sigma bonds or how many pi bonds are within this structure. All right, and that's going to be just knowing this table and saying, okay, how many single bonds do I have? All right, if I have 5 single bonds, then I have 5 sigma bonds. Do I have a double bond? And so on. And we'll do an example with that, all right? But knowing this table is going to help so much. All right, so let's do a couple here. We'll start with the first one. So we're just going to see how many sigma or pi bonds there are in this entire structure. So remember, we said that a single bond is a sigma bond. So in this case, we have 1. Actually, let me circle them. We have 1, 2, 3, 4, and 5. That's it. We have 5 sigma bonds. All right. So yes, it really can be that simple. Just knowing, what is a sigma bond consist of, what does a pi bond consist of, and so on. So let's do another one. So let's say here we have, that's a single bond. So I know, okay, that's 1 sigma. Same thing on the opposite side. And then what did we say? We said, okay, well, a triple bond is 1 sigma, and it consists of 2 pi. And let me not put it there because the answer is going to show up there. So this consists of 1 sigma and 2 pi because it's a triple bond. So how many sigmas do we have in total? Well, we have 1, 2, 3, and we have 2 pi bonds. And that would be our answer in this case. We have 3 sigma and 2 pi bonds. And then the last one goes back to how many pi and how many sigma bonds are in a double bond. So for a double bond, we said there's 1 sigma and 1 pi, and same thing for this other one. So then in this case, we have 2 sigma and 2 pi. And that's it. That's how you figure out how many sigma or pi bonds there are. So that is, I have seen that as like a multiple choice question or just like an additional, those when they give you like a whole page of questions and it's really just like the first question, like A, B, C, all these different parts. I've seen something like this in there. So just beware of that on your next exam. Next thing is how these orbitals are overlapping. Remember I mentioned that hybridization is really focused on the overlapping orbitals and how we see, how we actually see if S is overlapping with P or is P overlapping with another P orbital and so on. So here, this is going to be a little bit more in detail where our sigma bonds are always going to be the horizontal overlapping. All right, so think of it as a sigma bond is going to be horizontal. So in this case, we'll have an S orbital overlapping with a P orbital. And then we would have had something else here. And specifically, by the way, these are typically called PX. I'll go over that in the next slide as to what everything is, PX, PY, PZ. I'll touch on that in a second. But I just want you to think of this. This is what a sigma bond looks like for our overlap. Now for a pi bond, that's going to be a vertical overlapping of orbitals. So in this case, we'll have, like, let's say PY and PY overlapping or PY and PZ overlapping. And it's just horizontally, and that's what tells us that it is a pi bond. So let me touch on that again, and I'm going to draw everything. Okay. So if we were to have an S orbital, and by the way, remember guys, this goes back to electron configuration. So where this is an S, P, D, and F orbitals that we have. So an S orbital, there's only one orbital, right? An S, really these are our subshells. These are our subshells, and then this has one orbital within that subshell. So this means that we have kind of like that sphere-looking orbital. Now P is going to have 3 different orbitals. Let me actually draw that a tiny bit differently. I'm going to draw an actual axis. So this is going to be Px, Py, and Pz. There's 3 different orbitals within the P subshell. So our Px is going to have 2 different lobes, or really, this is what I want you to think, that's a lobe, on the x-axis. And then Py is on the y-axis. Now for Pz, that's on the z-axis, so it's going across. That's essentially what it's going to look like, all right? So then this is what's going to help us understand how to draw everything for our hybridization. Okay, let's do this now for this type of example. All right, so before I could even draw everything, the first thing that I want you to do is to actually write out the electron configuration for carbon and for hydrogen. And the reason why we're doing that is because we're going to draw an orbital diagram. And if we remember what all this means, okay, I know this is piecing everything together. An orbital diagram, remember if it was like hydrogen, I know hydrogen is 1s1 for our electron configuration. Well, that tells me there's only one orbital, and there's only one, actually, there's going to be there's only going to be one electron in that s orbital, right? And then now for carbon, if I were to go back, and I think I have another slide, perfect. So going back to electron configuration, just real quick, understanding how to do this, our electron configuration, remember that the light blue is our S block, right? Same with helium. Here, the green is our P block, the orange is our D block, and at the bottom, the pink is going to be our F block. By the way, guys, tomorrow I will be releasing another video, or I'll be uploading another video, and it is on electron configuration. So if you don't know how to do that, I will be covering that tomorrow in my next video, all right, at 3:30 Pacific time. So still going to show you how to do that here, where if we're looking for carbon, right, carbon is right here. What we always want to do for electron configuration is we're going to start from hydrogen, and we're going to go from left to right. So from left to right, and then we're going to turn around and go to the second row. And then we're going to make our way all the way to whatever we're looking for, which in this case is carbon. So then what I would do is I'm going to start off with carbon we said was 1s2. Why? Because this 1 tells us it's the first row. And then remember, this is in the S block. So this has 1 electron, 2 electrons. That's how I got the 2. I'm going to come around. I'm now in the second row, and I'm still in that S block. And there's how many electrons here? Well, there's 1 and 2. So that's how I get the 2s2. Next, I'm going to keep going across. And now this is the P block, but I'm still in the second row. So I have that this is 2. That just means it's in the second row. And then next, it's at the P block, but I have to count up to carbon. So here, this is 1 and 2. So then that would have been 2p2, and we stop. So that's the electron configuration of carbon. That's the full electron configuration. I did see earlier that someone had a question on electron configuration. We don't abbreviate it if it's not asking for the abbreviated method, which is the noble gas method. If we're asked for the full electron configuration, we show the entire thing, okay? So this would have been our electron configuration for carbon. The next thing I want us to do is to actually draw this out as an orbital diagram, which I did here. Here we go. So we said hydrogen, and this actually should have been just 1 electron. So because this is only 1 electron, right? So for carbon, what I want you to see is I'm just going to look at the 2p, or the 2 row. So the reason why I'm just looking at the 2 is because that's the highest in energy. So in this case, we have 2s2 because those electrons are filled, so that's done. And then next, we have 2 electrons in our p orbitals. What that tells me is there's only 2 electrons in that p orbitals. So I will not have a 2pz. Instead, I will only have a 2px and a 2py. Remember Hund's rule, when we're filling these electrons, and I'll put them here. So when we're filling these electrons don't like to be next to each other. Think of it as if you're going to sit at, I don't know, at a crowded place, or if you just want to sit at a table, I don't know about you, but I personally like to have my space, and I will sit away from people. I'm not antisocial, I promise, but I will sit away from people. So think of electrons like that. They want to be away from one another, and that's what Hund's rule is essentially saying, where this is just one. It's not going to be like that. Instead, it's going to fill the other orbitals first, and then come back around. So in this case, I just had 1 and 2. Okay, so let's go back and see how we can now draw this. Because we stated that hydrogen has that 1s, right, 1 electron there, and that carbon has a 2s and a px-py, does not have a pz, this is what we're going to do. So hydrogen has an s. Remember that an s is like a sphere-like shape. So this is going to be that sphere-like shape. And then next, carbon, each carbon, we'll have I'm going to focus on the higher energy one, the p orbital. So because it's px, remember px is on the x-axis. So then this is how I'll draw it. This is px and px. We have that overlap, which is great because that's what hybridization is. And then remember this type of overlap, that horizontal overlap where there's an s and a px orbital, those two overlapping is going to give us a sigma bond. So that's our first sigma bond. And then, which makes sense because this is a single bond, right? A single bond is a sigma bond. And then now we'll have the same thing on the opposite side where this is a px and px that are overlapping. So this tells us, okay, there's also a sigma bond here and a sigma bond here. And this should make sense because remember that triple bond gives us 1 sigma and 2 pi. And we'll get to the 2 pi in a second. So next thing I want to do is show that py. So that py is on the y-axis. So then this is here. So I'm just drawing it in. And then what we'll notice is remember that your pi bonds is actually going to be the overlap that is vertical. And specifically, it would either be two py orbitals overlapping or a py and a pz overlapping. It's just that vertical overlapping. So this is our pi and this is our pi. So then that easily kind of tells us that, okay, well, I have a sigma, I have 2 pi's, and this is the more, I'd say, complicated, but a little bit more exact way with hybridization, and that's why that shortcut works that I mentioned previously, where, okay, a single bond is a sigma bond, and so on. Well, that is essentially showing you how everything is hidden within the molecule when we actually draw this out. So I do have a prettier picture of this. This would be the overall structure of how everything is structured together for hybridization. All right, so I hope that's making some more sense. We're going to go into the last question, which is standard enthalpy of formation, as I take a sip of water. All right, so this is going to be our main formula. As always, know your formulas. Those are going to be extremely beneficial. Let's explain what this formula even means. So, and then even before that, I just want to mention what enthalpy is. A lot of times they tend to, I remember a lot of my chemistry books would overcomplicate what what enthalpy is, or really any sort of definition. So what I want you to think of enthalpy is essentially heat transfer, all right? The transferring of heat. So that's going to be the easiest way to think about it. So it's represented as H, and then what I want you to see here is that N is going to be the number of moles. All right, so moles, or remember what that essentially is just the coefficient that is in front of our molecule or compound in our balanced equation. Okay, so that's essentially it. Whenever you see mole or N, it's typically moles. And then now this is telling us the summation, or really just tells us that we're going to add up all of the products. So all of the values, this tells us it's the standard enthalpy of formation of specifically the products minus the sum of our reactants, the standard enthalpy of formation of our reactants. So I'll go further into what this is all saying. Now, let's say if they gave you something like this. This is a common question that you could be given, and they're asking you to calculate the overall enthalpy, standard enthalpy of formation of our overall reaction. All right. So for this reaction, so I already have all of my N's, right? This is 2, 5, 4, and 4. Those are going to be N, or the amount of moles. They will also provide you with a table because they have to. You are not expected to memorize this, thank goodness. So you will have to have a table. They might even give you it at the end of your exam, like kind of like a table that you'll see. And then it will just give you the actual values for the standard enthalpy of formations. So then what I'm going to do is I'm just going to bring back that formula. And then we're actually going to apply this. So what I want you to see is, let's start off with our products. So it's always products minus reactants. So our products, I would have placed a 4, right? Because we have that N, so I would have placed a 4 here. And then I would have had, okay, well, I have to have the standard enthalpy of formation of carbon dioxide. I would add that to the other, our other one that we have, which is water. So 2, standard formation, I forgot my little standard symbol, of H2O. And that's going to be my product here. I would subtract that by, I'm going to run out of room, but I have it on the next slide. I would subtract that by the sum of my reactants. All right, so that's essentially what we're doing. Let me show you that. Perfect. So this is what we would have. All right, you'll see that, and I think I wrote all over this. Perfect. Let me see if I can erase this part. Okay, so here we go. It's really just about knowing how to use your formula. So as I mentioned, here's the 4, right? There's the 4. We have our carbon dioxide. I'm going to add that to 2 times our water, our standard formation of water. And then same thing now, I'm going to subtract this by the sum of our reactants. So I have that 2 in front. I have my C2H2, and then I'll have 5 again with O2, the standard enthalpy of formation of O2. Next thing is to just plug in the values that they actually give you. So that's what we'll do next. We'll plug in all of the values just using the table that will be provided. So CO2 is going to be right here. And then I'm going to keep plugging in. So now I have this value for H2O multiplied by the coefficient that we had in front. And then C2H2, that's going to be 227.4. And then now oxygen O2 is going to be 0. Typically, by the way, just in case they don't mention it, which I don't see why they wouldn't, if it's O2 or any sort of diatomic molecule, then that is most likely going to have a standard of enthalpy of 0, okay? So that's going to be of 0. Like this could have been Cl2 or F2 or H2. So anything like that, that would have a 0 value, just in case they don't put that, okay? So then next, I would add everything together, actually multiply, and this would be our overall enthalpy of our reaction. Now, one little tip here, just in case they do ask, is this endothermic or is this exothermic, and what that all means. So because we have our standard enthalpy of formation, because that's negative. So whenever your delta H is negative, that means it's exothermic. And then there is a nice way that I kind of like to think about this if you ever forget what is endothermic, what is exothermic. Well, if you were to, and I want you to think of it as, I'm like here in like sunny California, but if, let's pretend that I'm somewhere where it's cold, okay, where it's like winter, where as we enter like our home, it's nice and warm. So when you enter somewhere, or endothermic, that means that you are absorbing heat. Okay, so you are actually absorbing heat when you enter somewhere, or that's an endothermic reaction is you're absorbing heat. Now, if you go outside into the cold, then you are exiting, or you're exothermic, because you are releasing heat into your surroundings and you're actually becoming colder. So that's how I personally like to think of it. Enter somewhere, it's typically warmer, and that is like inside, let's say your home, and then that would be endothermic. Exit somewhere else, it's going to be cold, and that's going to be exothermic, which is going to be colder, just meaning you're releasing the heat. Okay, so that's essentially what I kind of want you to think of. Another way of thinking of it as if it's exothermic, the heat is exiting out of you because you're becoming colder, right? So that's essentially how I like to just remember it. I don't know. I like to have all these little tricks for you. I know there's a lot that you guys have to memorize. So I'm seeing a lot of people asking questions of balancing equations, which I have plenty of videos for you guys for that. So let me see if I can pull up some videos. I actually just made a recent video on, I believe it was balancing equations with polyatomic ions. Yes. So there's a lot of videos that I'm trying to keep track of. I even have a playlist as well that I can put there too. So I'll put that on the chat for everyone that needs help with balancing equations. I do have several videos on that. Same with predicting products. I have several videos on that as well. So definitely check that playlist out. There it will explain in detail what you need to go over. And let me see if I can put my most recent video as well on, I believe it really was, balancing equations with polyatomic ions. Yeah, so many ones I have to keep track of. But yeah, so I'll put that in the chat right now, and let me see if there was anything else that you guys had questions on. But I did want to mention, as you can see on the screen, if you want your questions, a chance for your questions to get answered on the next Sunday, please tweet me. Tweet me your chemistry question. Take a picture of it. You could even type it out, or you can just say, hey, I don't understand Lewis structures. I don't understand balancing equations. And I will create a whole lesson or a little part of that lesson answering that question and doing my best to answer as many questions as possible in this time. So everything that I came, what I did here was because I had previous questions, previous tweets of people tweeting me and asking those questions, and that's what I pulled from. Right now, I would just say, really, tweet me your questions, take advantage of that, because not many people are, and then the people that are actually getting a lot of their questions answered every single week. So we will do that, all right? So I think I put that already in the chat. Perfectly, I did. So as you guys... So make sure to do that. I'm thinking what else I wanted to say. As you guys go throughout this week, if you have something that you're aren't too sure of, need some help with, tweet me. Really, tweet me. Now, if let's say you really need to have you need more immediate help, or if you just really need another resource besides my videos or besides the Sunday live sessions that I do every single week, then what I highly recommend to do is I have a bunch of resources in the description box of this video and every single video, really. If you look at the very bottom of the description box, you will see that I have different links that will take you to Chegg Study or Chegg Tutors, or really a lot of different resources there. I highly recommend checking that out if you are struggling with chemistry, or even if you're struggling with math, physics, really any sort of science topic. I highly recommend that. Why I say that is because I used it. So I personally used it all throughout college. I just don't know how I could have managed without it. I was really thankful to just use it overall. So that's why I personally recommend it. I only want to recommend things that I personally have used or I actually, believe in. So that's what I highly recommend checking out in the description box. You can find that at the bottom. Just a disclaimer, I am part of their affiliate program. All that means is that I'll get a little bit of commission if you do click the link. And all that goes to is my channel, helping support my channel so I can, make more videos for you guys, like the one that's coming up tomorrow. There's going to be another video coming up tomorrow on electron configuration. And then, of course, every single Monday I'll be posting more. So definitely check that out, guys. There are so many resources that I always have in the description box. And I hope to see you guys next Sunday. So tweet me and I will see you guys next Sunday. Have an awesome week, guys. See you guys.